Okay, before I forget, we'll start out. So I'll post an answer key to that first Excel assignment up on Canvas today. I'm going to create like a folder, and it'll just have all the Excel files in it, and then also the answer key. So you can kind of look on and see how maybe some mistakes you made. I'm going to have my GAs help me grade that. So I don't know exactly when it'll be graded by. I'm hoping kind of by the end of this week. Because I'll also be putting up some practice exams for kind of that first exam. So a little bit in the future, but I'm not expecting maybe even to look at those necessarily this week, but I'm just going to get them up there early because we're also going to have one more Connect and one more Excel assignment for that exam, okay? So those will be due the end of next week, right? So I would suggest trying to work on those this week, right? Get those out of the way. We really shouldn't have a lot of new material next week. It'll probably be a lot of me just working through additional problems, kind of going through some of those practice exams. But we will have those two homework assignments. So like I said, I would try to get those kind of out of the way this week. They'll be about the same length as before. The Connect will be about 13, 14 questions. And then the Excel probably, I don't know, maybe it would take less. It kind of depends. It'll take around the same or maybe a little bit less time in the first Excel assignment. It'll be what we did basically building those contingency tables. That'll be the 80 to 90% of that Excel assignment, okay? Other than that, are there any questions for me before we get started? Okay, we're good. Am I sounding okay on Zoom? I had a little bit of an issue last class.
Yeah.
Okay. And to reset it. So if it gets bad at any point, make sure you speak up and I can try to get that reset. All right. So we'll jump into it. I'll probably go pretty quick through the first part of this class because a lot of it's going to be kind of review or stuff we've done but painted in a different light, okay? So we're going to talk about random variables, which is basically just some variable for which the outcome we don't know yet, right? It hasn't occurred. We can look at previous outcomes of the experiment, but this is going to be something that hasn't occurred yet, okay? We're going to have discrete and continuous random variables, just like we had discrete and continuous regular variables, right? The way that we're going to notate this random variable, we're going to write as capital X, okay? Each one of the outcomes that we could see this variable be, we're going to denote as X subscript 1, X subscript 2. So if we think about maybe an example, this is the number of kids in a household. If I'm asking a family at random, well, the number of possible outcomes, I could think about the first outcome I could see could be 0. The second outcome, X2, could be 1, then 2, then 3, so on and so forth, right? So these discrete random variables, typically, right, we've talked about kind of the idea of being discrete. It's a finite number of responses or like a small number of responses typically. We can only see integer values. So this is where we said we could see 0, 4, 8, but we're not going to see 6.42. Okay? So nothing kind of really different from what we had talked about prior. It's just now it's a discrete random variable instead of a discrete variable because it hasn't occurred yet. We know what the outcomes could be, but we haven't run this experiment yet. I haven't asked a random household yet how many kids are in the household. Or, we thought about how many times do you do a certain activity a week, 0 through 7 days would be the possible answers you could see there. Okay. I'm not going to go waste too much time with this because we won't talk about continuous random variables until after the exam. But this was the idea that, we could see those values in between, right? Like I said, we're not going to do anything with these until after the first exam. So we're just going to focus on, these guys here, the discrete random variables. So some examples that we can think about, family size, I've already used this one, like the number of children, the number of dependents on a tax return. That's going to be discrete, right? I can't see 1.5 kids, or hopefully I don't see 1.5 kids. Distance was one of these ones that's continuous because we can measure it out to whatever decimal. But then one that we might start to see pop up, it's a little bit different, I think, than what we've talked about prior, is I could have a qualitative variable. So do you own a dog or a cat? Possible responses, I own neither. I own only a dog or dogs. I own only a cat, or I own both types of animals. Right? So technically, that's a qualitative variable, right? The response will be some word. But if we saw these qualitative responses, we could turn them into numerical values. If these are the only 4 possible responses, I'll call owning no pet a 1, owning only a dog 2, so on and so forth, right? So we essentially can force that qualitative variable to be discrete, right? So that we can get some numerical calculations or statistics from it, okay? Any questions? That should be kind of easy. So what we're going to want to do is build a probability distribution for all these possible responses. So I want to see a distribution for the number of children in a household where I can look and see what's the probability I see 0 kids, what's the probability I see 1 kid, the probability I see 2, so on and so forth, right? Now I could display that in a table or graph, and hopefully we'll kind of see in a second. That's pretty easy. It's also something we've pretty much already done. Or I'm going to have a function, which we call the probability mass function, that tells me the probability as I plug in different x values. So this probability mass function, in theory, if I could plug a 0 into it, it would tell me the probability of having 0 kids in the household. If I plug a 4 into it, the probability I see exactly 4 kids in the household, right? So we're going to call that, kind of write that as capital P of x, right? Instead of like usually f of x is our function, here we've got capital P of x indicating this is giving us a probability of seeing that particular outcome. Okay? So that probability mass function, as we plug in different values for x, it will give us the probability that that random variable takes on that value. The probability that random variable is equal to 2. It'll spit that probability back out at us. Plug a 4 in. It'll spit back out at us the probability that x is equal to 4. So if we did that, you can think about, I'd have a bunch of different values, right? Maybe for the kids example, I don't know, something like 0 through 12. I don't know, there's probably some household with more than 12 kids, but you get the idea. For each value there, 0, we'll plug that into our probability mass function. It spits out as a probability. We now have an XY pair, right? I could plot on the x-axis that value of 0 and then draw a bar up to whatever the probability is. Then I have the next outcome I could see is 1. Plug 1 into that probability mass function. Use that probability to draw the bar up for that outcome of 1. And then do that all the way up to, the highest number of kids I could possibly see. And I essentially have a bar graph. It would look kind of like those histograms we did, right? That would tell me the distribution for that random variable of the number of kids in a household. Okay? If I think about these probabilities, right, I know they have to be, well, the lowest probability I can see is 0, right? It's probably, if nothing can occur, like we just know it can't occur, the probability it occurs is 0. It's the lowest we can get. And then something that is certain, or we know for 100% certainty that it's going to occur, that probability would be 1, right? So we know that this function is going to spit out at us values somewhere in that range, okay? Now, it's very unlikely it's going to be exactly 1. That wouldn't be a very interesting example. Like, you would know the outcome. Like, why do we have to do anything? I already know what the outcome is going to be. And well, that might make a little more sense when we start talking about the expected value of a random variable, but likely it's going to be somewhere in between that range of 0 and 1. Right? It's unlikely it'll be exactly equal to 1, but it is theoretically possible. What also ends up being true, very similar to what we did with histograms, when we created relative frequencies, we said if I go through every possible bin, right, and I add up all the relative frequencies, or every possible response, we think about the entire experimental outcome space. When I said add up the probabilities of every possible outcome, those probabilities should add up to 1, right? It should fill out the entire experimental outcome space. Same idea here. If I look at that probability mass function, it's just going to tell me the probability of seeing the very first or the lowest outcome, then add to that the probability of seeing the next highest outcome, add to that the next highest, all the way to the very last possible outcome. Well, those probabilities, I've added up the probability of every possible outcome. Those always should add up to 1. Right? And as we work through a couple of the examples, I'll make sure I kind of point out, and I think that becomes a little bit more intuitive. Okay? So, like I said, these probabilities, we can kind of think about them as relative frequencies, right? So we could plot them, and very similar to relative frequencies, we also talked about cumulative relative frequencies, right? So a cumulative mass function, right? This is the idea of look at whatever outcome X you're plugging in and add up the probabilities of that, seeing that outcome, and every outcome that's less than that, right? Every outcome below it, okay? So I'll write something out here in just a second that'll help with this. But basically, if I'm thinking about the number of kids, and I think I plug a 3 in here, what that's really saying is what's the probability I see the number of kids in a household be 3 or 2 or 1 or 0, right? Basically, all the outcomes that would fit that criteria of x being less than or equal to 3. So I find the probability that x is equal to 3, then I would add to that the probability x is equal to 2, plus the probability x is equal to 1, plus the probability x is equal to 0. Okay. So as I move down towards those lower values, that cumulative mass function will be closer to 0. As I move to the higher values, that cumulative mass function approaches 1. In fact, when I get to the highest possible outcome, so like let's say I plugged into my cumulative mass function for the number of kids in a household. Let's say I plug in 20. The probability I see the number of kids in a household be 20 or fewer is probably exactly 1. I don't know if there's any household that has more than 20 kids, right? So when we get to that very highest possible outcome, our cumulative mass function actually should be 1, right? So let's look at an actual small data set and we can kind of start to talk through this. Actually, I lied. Before we do that, I want to show you something to kind of get at this idea of cumulative, because we'll start using it. Actually, I think based off last section, we'll end up using it more next class, but I want to set us up to be able to think about these cumulative mass functions. So let's say I did want that probability that x is less than or equal to 3. Okay. What I'm really thinking about there is, okay, what's the probability x is equal to 3, or x could be 2, or 1, or 0, right? I can't say anything less than 0, right? I can't have negative kids in a household. Okay. So remember we said if I'm ever looking at a union of two things, this or this, it's the probability of each event, add them together, and subtract what you double count, which is the intersection. Right? Here is an interesting example where what's the probability that I could see, like, so let's say I'm looking for the probability of x is equal to 3 and x is equal to 2. So what's the probability that if I look at the number of kids in a household, I see exactly 2 and I see exactly 3 kids in that household? I can't. It's one or the other, right? These are mutually exclusive events. I'm only going to see one exact number of kids in a household. So all my intersections here between these events are 0. So this simply becomes add the probability up of all those events, or the probability x is equal to 3 plus the probability x is equal to 2 plus the probability x is equal to 1. I'll be real thorough here on this one and write it all out, right? All the way down to 0. Right? And it kind of hinges on that idea that we already talked about, which is that if they're mutually exclusive events, we get to actually ignore the intersection. So that's kind of nice. Okay. Any questions on this? Okay with this? All right. So let's say I had this data set. I think there was a small typo maybe in the lecture slides that I posted. This said like wins, just replace it with hires. I want to set this up to talk about, like, let's say I had some company and they're trying to project how many new positions they think they might have this next year. Well, if like COVID and stuff wasn't going on, let's think about like this is like a regular year, right? So they look at the last 35 years of data from their company and they say, how many years in the last 35 years did we hire no one? So they count. There was actually 0 years where they hired no one. How many years did we only hire one person? 2 years. How many years did we only hire 2 people? 1 year. How many years do we hire 3? There's actually 7 years in which we hired exactly 3 people. So on and so forth, right? So how could I use this information to build a probability mass function essentially for the future? Well, it's just like we did, similar when we were looking at like histograms and kind of even thinking about qualitative variables when we're looking at distributions. Also with the contingency tables. If I have frequencies, how could I turn those into probabilities? Divide by, if 2 out of the last 35 years I've had exactly 1 hire, the probability based off of historical data that I hire exactly 1 person would just be 2 over 35, right? So if I divide these frequencies by the number of observations here, I could produce the probabilities of seeing all those different possible outcomes, 0 through 12 here. Now, I kind of built this out, but notice there are some outcomes that have a 0 probability of occurring, right? And this is, we've built this probability mass function based off of historical data. So we talked about empirically assigning probabilities. So that's what we did here. So notice for these higher value outcomes, they are still possible, like we thought they were possible to see, but once we actually look at the data, the probability they occur is actually 0. Okay. Notice if I look at every possible outcome and I add the probabilities up of every possible outcome, those add up to 1, right? Because there, if you think about like the cumulative density function, we're really saying it's like, what's the probability that I see the number of new hires be 12 or 11 or 10 or 9 or 8 or 7 all the way down to 0? Well, I have to see one of them. So the probability I see one of those is going to be 1, right? I have to see one of those outcomes. So that's essentially the idea of if we add up the probabilities of every possible outcome, they'll always add it, or they should add up to 1 if we've done things correctly. Okay. Any questions up to this point? Like I said, I know I'm working a little quick through this, but it's, like I said, this is looks really similar to what we've done before, right? We just think about these as relative frequencies. It looks like what we've already done. So I could use those X values, and I mentioned earlier I could just use my probabilities to plot these bars, right? And then I get a nice idea of what the distribution of this variable looks like, or the probability distribution of this random variable. It kind of looks like here, 3 and 4 are the most likely outcomes, but I see, some outcomes that are above that be a little bit more likely here than the outcomes below it. Right? So if I'm trying to think about, where's the middle of this data kind of lie, or where does what's the average outcome I typically see? I'm looking here, it's probably somewhere around 4 or 5, I don't know, somewhere in there. But how could I actually compute it, right? So how do I find the mean of these discrete random variables? Well, it's going to be pretty easy. One thing to get out of the way, the two interchangeable terms here. Once we're talking about the mean of a discrete random variable, another word for that is the expected value, right? Because we're no longer like computing like the mean. We're trying to predict the future, right? Right. Well, the whole idea about the new hires, we're trying to predict the number of new positions we'll hire for this coming year, right? Something that hasn't happened yet. So sometimes we'll, instead of calling the mean of a discrete random variable, we'll call it the expected value, right? So we'll write it here just like we always write the mean. Oh, you guys gotta let me know that didn't switch over. Hold on. Where was I at when I was stopped talking? It was like right here. So Zoom, you guys have been okay, but in class they were looking at what I had written down before. So here was the data, right? How did I turn these frequencies into probabilities? I just divided by that total number of observations, right? Then it's just a matter of plotting these X values using the probabilities as the Y value, and that's how we get these bars. Okay? So this is where I was talking about, what does it look like the middle of the distribution is? Probably somewhere around 4 or 5. Hey, you guys gotta speak up, now I feel bad. But this is like nothing new, right? This is like stuff that we've kind of already done with relative frequencies. It's just now we're trying to predict something that's going to happen, right? So when we try to find the middle point of that data, instead of the mean, we'll sometimes call it the expected value. So we've got the mean here. That's how we typically write it, right? Mu, and we'll just call it X of this random variable, the mean of the random variable X. Or we can write it as the expected value of this random variable X. Okay? Those are kind of interchangeable terms. So once I think about finding this middle point of the data, right, this mean, I'm going to write it out more formally. It's something that looks very similar to what we've already done. So to find that expected value or that mean of the random variable, I'll go through every possible outcome. I'll multiply it by the probability I saw that outcome occur, and then add them all up. Right? So this looks something. What does this look like? There's something that we've done that's similar to this. What does this kind of look like? What if I just replace the probability, think about that as a weight. This looks kind of like a weighted mean, except that we don't have a denominator, right? But if we remember, with the weighted mean, if our probabilities are now these weights or our kind of frequencies that we're using, what would the sum of these probabilities be? Well, if it's across every possible outcome, the sum of just the probabilities would be 1. So that denominator would always be 1, so we essentially can kind of ignore it. So finding the mean of a discrete random variable, is essentially finding a weighted mean where the probabilities are your weights. And so you know the denominator, the sum of the weights, or the sum of your probabilities should always be 1. So it's almost like a little bit easier than the weighted mean, really. Okay. So I'll show you an example here. Really simple. It kind of gets at this idea of expected value. So a lot of times when you make an investment, right, you want to know what the average kind of payout's going to be. Kind of what my expected revenue, like I know that there's all these things that could occur. They all have these probabilities of revenues this high or this high. What's the expected kind of revenue in the future, right? Or the expected payout from a certain investment strategy? So I like to think about this as like, what if we looked at like a simple lottery example, right? So instead of like a massive lottery, because I don't know the probabilities off the top of my head, won't come make these up, but let's say I play a lottery, like a 50-50 raffle. If any of you have ever kind of heard of one of those, basically you buy a ticket and they pull all the tickets in a bowl, and then you win like half of however much was spent, right? So they're a way to raise money. It's essentially the same thing as a lottery. So there is a chance that you lose and you spent $1, so your payout there would be -$1, right? I didn't win the lottery, I didn't win the raffle, but I bought a ticket. Then to make this easy, let's say that the winner of that raffle ends up winning $501. So you spent $1 to buy the ticket, you win 501. So kind of your other outcome you could see is that I like won 500, right? I got my dollar back and then I got an additional $500. Let's say the probability that you win, say there's 1,000 people. So your chance of winning is 1 out of 1,000, okay? Which means the probability you lose, and we're assuming everyone can only buy one ticket out here, I guess, but the probability you lose is 0.999. So I have 2 possible outcomes here, and I know the probabilities that they occur. To find the expected value or the expected payout of playing this raffle or lottery, all I do is I could just lose the $1 that I bought, I bought the ticket and I didn't win. The probability that occurs is 0.999. Right? So the majority of time, I'm going to lose $1, right? However, sometimes I'll win that 500, but the probability I win that 500 was just 0.001. So the expected value, if I end up, plugging this into my calculator, I think it's like -0.4999. So roughly -0.5. Now, this is an interesting example to point out a few things. One, if I'm playing this lottery, what is my expected payout? -50 cents. So on average, I'm going to lose money if I play this or enter this raffle, right? Now, if I can only buy one ticket. Now, the problem is, if we think about, can I actually lose just 50 cents? No, I either lose $1, or I win 500. So it's kind of odd because these means or these expected values for these discrete random variables are likely not an outcome you can actually see. It's just the average of the possible outcomes, right? On average, I'm losing 50 cents, right? Which means more likely than not, when I look at these outcomes, I see a lot of negative ones, and then occasionally I'll see 1/500 or something like that, right? So it's a little bit tricky because when we find these expected values, they may not be an integer, right? They may not be one of the possible outcomes we can see, but it's still a measure of like the mean or kind of where the central point of these outcomes are, right? Before we said it was a central point of the data, now it's like the central point of where those possible outcomes are. Any questions on this? Like I said, we want to kind of think of these were our X values here, and these were our probabilities that they occurred. Right? So all we did was multiply each outcome by the probability that occurs. Okay. So if we go back, if it switches off the slides, let me know. Now we'll go back and think about this data set we had, right? So what if we wanted the mean number of new hires? All we could do is go through, take each outcome, 0 times 0, plus 1 times 0.06, plus 2 times 0.03, right? And just do that for every possible outcome, right? Once we add all those up, we get about 5.14. Okay? So this was very similar to a weighted mean example. I don't think it's a whole lot new here, other than we don't have a denominator to worry about, which is nice, okay? And that kind of makes sense, right? When we were looking at that distribution, we said the middle of the data looks like it's somewhere around 4 or 5, but we have some of these higher values that maybe pull the mean up a little bit. And think about which of these outcomes will influence the mean the most. So we got that mean of 5.14. Well, the more likely outcomes, right, are going to influence that mean more than the unlikely outcomes, right? The outcomes that had a probability of 0 occurring actually don't affect that at all, because 0 times anything is 0, right? Any questions on this before we keep moving? Shouldn't be too bad, yeah. You can kind of guess. If we can find a mean, we can find a variance, right? So just like we have the mean of a discrete random variable is like a weighted mean, the variance of a discrete random variable is very similar to a weighted variance, right? You just go through every possible outcome, you subtract the mean, square that value. Once you have that deviation from the mean squared, multiply it by your weight, which is a probability, right? That probability mass function value. Do that for every possible outcome, add them all up. There's nothing to divide by because the sum of your weights, or the sum of the probabilities, is still 1, right? So it's just like a weighted variance equation, but with no denominator, okay? Just like with every other thing, if I want to go from my variance to my standard deviation, the only thing I have to do is take the square root, okay? And I'll show you some examples of these as well, like some smaller examples in a second. But any questions at this point? So it should kind of be a review. So let's say I go through that new higher data. All I do is go through the very first possible outcome of 0. I subtract that mean, which we found previously, which was 5.14, square that deviation from the mean, but then multiply it by the probability I see a 0 occur. Go to the next possible outcome of 1, subtract that mean, square it, multiply it by the probability I see a 1 occur. So this is exactly what we did with the weighted variance. It's just now we don't have a denominator. So we do it for every outcome, add them all up. Looks kind of like a mess, right? There's a little bit of work to do here. But this was kind of we had 13 possible outcomes here, really. Okay. Any questions on that? And if I wanted to find the standard deviation, what would I do? Just take the square root, right? Square root of 5.38. Okay. Try to hammer that one in because we're going to be just using it all throughout the semester. So let's work through some smaller examples. Oh, and I did this for the last class, so I want to get rid of this here, and I want to build this for you. I forgot to close out and then open it. So let's say we have this example where we want to find the mean bonus amount. Right? So I'm looking at these possible outcomes. I'm looking at these possible answers, and my possible outcomes range from I either see $0 as the bonus amount they get, and I kind of made this kind of a wild example, but 3 million, 6 million, or $10 million, right? I could change this to K if I wanted to, right, to make it a little bit more applicable to a normal job. But think about this huge kind of investment trading company, and the probability I see these different bonus amounts are right here. So all I'm going to do to determine what the mean bonus amount is, or the mean of this discrete random variable, is take each outcome X and multiply it by the probability, I didn't mean to capitalize this, and multiply by the probability that I see that outcome for X. So I could do, the intermediate step and just insert another column here and do my work right next to it. So this value, outcome of 10 times 0.15, or 10 million times 0.15 is what? 1.5, right? 10 times 0.15. 6 times 0.25 is 1.5. 3 times 0.4 is 1.2. And then 0 times 0.2, well, 0 times anything is 0. Right? Now it's just a matter of adding those values up. If I add those values up, I get 4.2 million. Okay? Or 4.2, and remember these are all in millions. Okay? Now, if I just looked at the data, make this a little bit bigger. The most likely outcomes, the two outcomes with the highest probability of occurring, were 3 and 6 million. So I'm probably thinking about my mean is going to be somewhere in between those two values. Okay? Maybe a little closer to 3, maybe a little closer to 6. I don't know exactly. Looking at these numbers, I can't envision it. But knowing the two most likely outcomes are 6 and 3 million, it's likely my mean is going to be somewhere in between those. Remember, this mean is supposed to be some measure of like where the middle or the average outcome is, right? Or the middle point between all these outcomes. So we get 4.2 million, right? That kind of makes sense, right? That was in that range, okay? I'm thinking about the possible answers of A and B here. Those don't really make a lot of sense. I mean, for the mean value to be as low as 250,000, I mean, 0, would have to have a probability of occurring of like 0.8 or 0.9, right? It'd have to be very we'd have to be seeing 0 most of the time so that the 0 would influence the mean more and kind of pull that mean down, right? So probably, looking at this, probably could rule A out right away. And really B is kind of a similar story. It's a little bit higher of a value, but based off of 3 and 6 million being the most likely outcomes, thinking B probably isn't a very likely answer either. Any questions at this point? Okay. What if I wanted to find the variance, right? So remember that the mean was 4.2 million, or 4.2. Well, first of all, can I rule out any of these answers before I even jump into the equation? Yeah. Yeah, why? It's different than the rest. Yeah, so we talked about with the variance, because we square the deviations, everything's always going to be positive that's getting added into the numerator. So we can never see a negative variance. It has to be 0 or higher. In fact, what would happen, this is kind of a weird thought experiment, but the lowest we could ever see the variance be is 0. I think we talked about that before. But with a discrete random variable, how would I have a variance of 0? So with a regular variable, we said, what would the data set have to look like with a variance of 0? Remember, the variance is kind of this measure of how far from the mean. So if the variance is 0, that means every value is the same, which for a discrete random variable, that would mean that all the outcomes are the same. So there's only one outcome, and the probability of seeing that outcome is 1. All the other outcomes have a probability of 0 of occurring, right? I can only see one value. So for a discrete random variable, a variance of 0 would mean there's one outcome that has a probability of occurring of 1, which is not an interesting example. So we'll probably never have a variance of 0, right? Why are we trying to make projections if we already know the probability is 100% of something occurring? So, but there, right, we can rule out B because we know they can't be negative. So from there, it's just going through each observation, taking that outcome X. I hate that it capitalizes that. I'm going to go back and change it here. There we go. I'm going to subtract it from the mean from that X value. Okay. I'm then going to square that deviation from the mean and then multiply it by the probability that the random variable X took on that specific outcome. Okay. So for that first one, that would be 10 minus 4.2. Square that deviation from the mean, right? The mean was 4.2 there. And then multiply it by the probability I saw 10 occur, which is 0.15. I'm then just going to go ahead and do that for every single observation, right? And then add them all up. Okay? So I could create this additional column. If I didn't want to do something like this, where I'm writing it all out on one line or one formula, I could kind of create this additional column, do this for every observation, write the values down, then add them all up, and that would give me my variance. Okay? If I do that here, I think you end up getting 9.96. Okay? Any questions on that process? Like I said, it's really like we've done this with weighted variances pretty much already. Does anybody know what movie this is, by the way? Yeah, right? So if you guys haven't seen this movie, especially being like business majors, first of all, it's just a really good movie, but it kind of explains the financial crisis where like the mortgage-backed bonds, but it does it in like a really easy to understand way. Like my sister can understand it, and she's like the most bohemian hippie, like anthropologist. Like she's not in this world at all, and she liked the movie. So I always like to, The Big Short. Yeah, it's pretty good. It's got like a high name, Carell's in it. This isn't Bradley. Who is this? Everyone likes him. Ryan Gosling, right, is in it. There's a lot of big name actors. Christian Bale's in it. So it's really good and explains it in like a really easy to understand way. And like if you're in the business building, you should kind of understand what was going on with that. I think it'll help you make better decisions in the future. Okay. All right, so we're going to really switch gears here. But I like this, so I don't know. I like this subject a little bit more. I don't love the. So what we were doing before was like we had this probability mass function, but it wasn't really a function, right? There was no functional form. It wasn't like a plus b times x squared plus c times x cubed. It was just we were taking data and empirically, assigning those probabilities, which is interesting, right? It's good that we know how to do that, but there's going to be a lot of scenarios that we have an actual function for our probability mass function, right? So we're going to set up these examples that we call binomial distribution examples. We're going to run some experiment n number of times, and we're doing it the same way every time. So this could be like, today we'll pretty much just use flipping a coin. So I flip a coin 100 times, right? Every coin flip is the exact same. And I'm just flipping a coin. It's the same experiment, and I'm doing it 100 times. We need to have an example where there's only two outcomes, right? So if I flip a coin, it's heads or it's tails, right? Or success, failure, right? So the success is just what you're looking for. So if I want to know what's a probability, of getting a certain number of heads out of 100, I'm looking, my success is seeing a heads on that coin flip, right? We'll walk through a lot of different examples though, where we kind of think about these success failures differently, but it's basically a binary outcome. There's only two things I can see. What also has to be true is for any one trial, the probability of success is the same. So for my coin flip example, on any one coin flip, my probability of seeing a heads is 0.5, right? And that's the constant across all 100 coin flips. I also have to make sure that I have these trials are independent, right? And we'll talk about, by the end of the class, I'll kind of mention some things we've talked about with independence and relate it to this binomial equation. So if I'm flipping a coin 100 times, right? I think intuitively we know on average, about how many heads will I see out of those 100? About 50, right? Now, any 100 coin flips, it's going to change, right? Maybe I flip it 100 times and I see actually 60 of the 100 come up heads, right? Or, maybe 55 of them come up heads, right? Or I can think about like if I had a smaller number of coin flips, let's say I flip it 10 times, I could end up, it's not very likely, but I could end up flipping heads all 10 times, right? I know the probability is probably pretty low of seeing that, but it could occur. So what's the probability I would actually see 10 out of 10 occur? That's what we're going to use that binomial distribution equation to find. So if I have I flip a coin 100 times, what's the probability I see all 100 coin flips come up heads? Because it is possible, right? I'm sure someone out there has done it and it's happened, right? But it's very, very unlikely to occur. How unlikely is it, right? So we're going to use this probability mass function for the binomial examples to calculate those probabilities. So the probability of seeing a certain number of successes out of n trials, right? It's going to be pretty nasty. Right? So it looks something like this. But I'll walk through it, and hopefully once we start using it, it's not as bad as it looks. So the P here is just that underlying probability of success on any one trial. So if I'm flipping a coin, my P there would be 0.5. The probability I see a heads on any one coin flip is just 0.5 here. Okay? N is the number of trials. Right? So if I flip a coin 100 times, my N would be 100. Right? And let's say I'm interested in finding the probability of 60 of the 100 coin flips come up heads. Well, that's 60 successes, right? I'm defining seeing heads as a success, so my X would be 60. Right? So the number of outcomes I'm interested in finding the probability of, that's my X. Number of trials is N, and that underlying probability of success for any one trial is P. Now, one thing that matters is, we're finding the probability not of seeing 60 successes, it's 60 successes out of 100 trials. If my N becomes 1,000, well, then the probability I see only exactly 60 heads out of 1,000, well, that's dramatically different, right? So N matters here. The number of trials matters. So really this part of the equation is just some simple addition, subtraction, multiplication, or not addition, subtraction, multiplication, and taking things to some powers, okay? This is probably what we're not as familiar with, right? These factorials, okay? So we've identified these three things. All the factorial is take that number and multiply down to 1. That's the easiest way to say it and think about it. So if I have 10 factorial, 10 times 9 times 8 times 7 times 6 times 4 times 3 times 2 times 1. Right? I have 100 factorial, 100 times 99 times 98, right? All the way down to 1, okay? Now, here's like a more formal way of thinking about it, but it doesn't really matter for us. So there's going to be some weird things that occur here, and I'll show you an example. I don't know if we'll get there today, but for sure Wednesday, where 0 factorial, right? The way that we, you could dive into a math book on this, but 0 factorial, for the sake of what we're doing, just remember 0 factorial is simply 1. Okay? So if we ever have 0 factorial, that's just 1. So let's work through an example here, right? And I'll probably go through one more, and then should be good for today. So let's say I flip a coin 10 times. It's a bias coin, right? So the probability it comes up heads on any one coin flip is 0.4. I then want to find what's the probability that 4 of the 10 coin flips are heads. So what's my number of trials here? 10, right? I'm flipping the coin 10 times. My probability of success in any one trial is 0.4. And the number of successes I'm interested in finding the probability of is 4. Right? So N is 10, X is 4, and that probability of success P is 0.4. So I just plug everything into this equation, and now it's just a little bit of math. So if you're trying to do these factorials, a lot of calculators, you have a factorial button on there. So it's usually on like a TI 83 or above. I think there's like a math, should say like math on the key. And then you go over 3 and it's PRB or PROB, and then you go down and there'll be an exclamation point there. Different calculators are different. Usually it's under some type of a math key or a probability PRB on some calculators, it'll say. But once you get to those options, it'll usually have an exclamation point in there. If you're ever having problems finding on your calculator, first of all, before you email me, Google the brand, the type of your calculator and factorial button and see if you can find it that way. Because that's probably honestly how I'll find it for you. But if you can't find it, you're having difficulties, send me an email, because we want to make sure that you know where that button's at in your calculator kind of moving forward, okay? Now you could just type it out, right? 10 factorial here. I could type into my calculator 10 times 9 times 8 times 6 times 4 times 3 times 2 times 1. That's fine. But it's going to be a lot easier, especially with larger values, to know where that factorial button is. Okay? Now, one issue with this is that if you try to plug in something like, I think it's anything above 60 factorial, even on like a really nice calculator, it's going to give you an error, right? And the smaller the calculator, the lower that number is going to be, because that 60 times 59 times 58 times 57 blows up to be a huge number pretty quickly, right? So one thing that we can do to kind of circumvent that, right, is write this out and think about how we can kind of get around technology issues, right? First of all, if I plug this in, I get about 0.25. I mean, that's if you're trying to kind of make sure you can get this entered into your calculator correctly, because it is a little bit tricky with the order of operations. I always tell people sometimes the easier way to do these is like work backwards and also do the simple math in your head. Instead of having all these parentheses in your calculator, 10 minus 4 is 6. Like, I hope we can do that, right? So just put a 6 in there instead of like parentheses and, so do the simple math first before you can enter it into your calculator. That helps a lot. But what if we had a scenario based off what I just told you where, let's say I had 100 coin flips, right? And I'm interested in something crazy like, I don't know, what's the probability that 90 of them come up heads? Actually, I'm gonna make this example easier to really highlight this. Let's say 99 of the 100, right? So I want to know what's the probability if I flip a coin 100 times, I get exactly 99 heads. Right? Well, the probability of success on any one coin flip, we're back to using a regular coin, so it's 0.5. So let's just write out that binomial equation. So it's n factorial divided by x factorial times n minus x factorial times the probability of success to the x power, 1 minus the probability of success to the n minus x. Well, first of all, we can simplify things. I mean, this is 1, right? This would be 0.5, and this would be 1, right? That just makes it, if we rewrote that out, make it a little bit easier to look at and also to put in our calculator. But I just told you I can't put that in my calculator. So how am I supposed to do this, right? Well, if I write this out, 100 factorial is 100 times 99 times 98 times 97, all the way down to 1, right? And I'm just going to focus on this part of it because this is just, taking things to powers. I think we can do that in a calculator. So here, 99 factorial is 99 times 98 times 97, all the way down to 1. And then this ended up being 1 factorial, so just multiply by 1. Right? So this is kind of weird. 1 and 0 factorial end up being the same value. They're both 1. Okay? But now notice, everything 99 and below would cancel. Now all I'm left with is 100 divided by 1. Right? So yeah, it didn't look like I could enter this in my calculator, and I can't. It won't be able to find 100 factorial for you. But if I write that out and think about what would cancel, this simplifies down to just 100. So anytime you have these really large values, there's probably a shortcut like this, so you can circumvent the fact that, yeah, if you actually tried to compute these numbers, 99 and 100 factorial, you wouldn't be able to get those values. Okay? Any questions on this before I keep moving? Yeah.
Say like on the last one where you had a 10 factorial over a 4 factorial.
Yep.
Is it just 10 minus 4 and then be the factorial of 6? If you don't want to put it in your calculator?
So not quite right. So on top, so if we wrote this out, it's a good question. What you would have, if I can get another piece of paper.
10 times 10 times 8.
Yeah, so you're close, right? Maybe I'm misunderstanding what you're saying, but here we had 4 times 3 times 2 times 1, and then this was 6 times 5. Yeah, so everything past the 6, but you don't have 6 factorial, you have 10 times 9 times 8 times 7. Yeah, everything below 6 factorial cancels, right? But this isn't 6 factorial, right? This is like what's remaining after. Yeah. Yep. But yeah, like even if you couldn't find your factorial button and you think about cancels, this is a lot easier to do, right? It's only 4 numbers on numerator and denominator. Yep. 2 minutes. Any other questions on that? I think I'll save an example for next class because I don't want to rush it too much and I want to relate it to what we were talking about with independence. So next class, we'll do a lot more binomial examples. We'll start to think about cumulative probability mass functions with a binomial. I'll probably show you, we'll briefly look at Excel, maybe like for 5 minutes, how to use Excel to calculate binomials. But yeah, that'll be next class. So I'll get those homeworks up, the answer key for the first Excel assignment. I would start working on those homeworks as much as possible this week, setting us up and kind of getting ready, getting closer and closer to that first exam, okay? All right, be safe. Roads are supposed to be bad today, and I'll see you guys on Wednesday.